So, any questions from last time? Okay, so since I made a mistake in announcing the class properly, the change in schedule yesterday, I think maybe I should do a small recap of what we did, so that for those who missed or whatever. So what we did first was that we computed the lifetime of a black hole that evaporates. Okay, so that's the first thing we did, and then we showed. Yeah, then we discussed, so that lifetime, roughly speaking, the lifetime goes as m cube. So the lifetime of a black hole is going as m cube, and this is sometimes called the phase time. Okay, so, or time scales of this order, where the mass of the black hole or the entropy of the black hole changes by order on factors. So that time scale is what is called the phase time, and that's a big time scale. Okay, it's much bigger than for black holes which are about the mass of the sun. It's much bigger than the age of the universe, for example. I mean, many orders of magnitude bigger. So, and that's one time scale. Then we introduced another time scale which is called the scrambling time. So this is T page, if you like. So T scrambling was this time scale. Okay, so this scrambling time is the time scale when, roughly speaking, all the things stabilize and all you're left with is the Hawking radiation. Okay, so it's a much shorter time scale than the phase time, but it's still, so note that it can be arbitrarily large still. So we are always talking in terms of different scales. Okay, so this is okay. If you want to write it like this, you can call it, well, it's better to call it m cube, but yeah, let me call it m cube, that's better. G square m cube. So, so the point is that this time scale is much bigger than this time scale, but this doesn't mean that this cannot be large. As we know, black holes can be arbitrarily large. So this means that, let me call it R horizon maybe. So, or R Schwarzschild is better. I think I was using R Schwarzschild yesterday. So, yeah, and that means that this can be arbitrarily large. Okay, so, and L Planck is the Planck length. And some of these formulas are, I'm working, some of these formulas they're all easy to generalize to general dimensions and general black holes, but I think some of these are explicitly written for the case of 3+1 dimensions. Okay? So that's the two things that we talked about, and in some detail. And the second thing, and the thing that we said is that if the black hole evaporates, so the key point about black hole evaporation is that the calculation that Hawking does seems to be valid in regimes where the black hole is evaporating. So in other words, when the mass of the black hole is large, or or more precisely the radius of the black hole is large, the calculation that he's doing should be reliable. Right? Essentially because the assumption is basically that m Planck by m of the black hole is 0. This is the limit in which we are doing the calculation. And when the black hole is macroscopic throughout its evolution, it is essentially this approximation is true. So only in the very, if the black hole is formed semi-classically, its initial radius is quite large. Okay, and then finally when it evaporates, it's at best or at worst only at the very end of the evolution you have a chance of violating semi-classical physics. Okay, and the problem with information paradox is that by the time you get there, the mass is if a scale involved is m Planck, you have to explain the entire entropy. During this entire evolution of this radiation coming out, it looks like it's all thermal radiation, and at the very end you have this m Planck, which is a small amount of mass, and note that the black hole could have started with arbitrary mass, which means its entropy, or so the entropy that we are talking about really is it's precisely thermal entropy. The SBH that we write down A by 4G is really thermodynamic entropy. It's not quite entanglement entropy, but we'll make those distinctions a little bit more precise eventually. But nonetheless, it is a crucial fact that the object, if you want to explain the initial pure state from which the black hole collapsed and formed, you will need to explain all of its microscopic details encoded into an object of mass which is m Planck, which is tiny, right? M Planck is, of course, if you want to put it into an accelerator, it's huge, but as a mass it is, I don't remember exactly, I should, but it's some small amount of mass. It's like a few, let's say orders of a few joules, I mean, everything is few joules, but I think it is not significantly higher than, let's say 100 joules or something like that. So it's completely wrong possibly, okay? I'm just randomly saying things. But anyway, so it's not huge, okay? And that's the point. And the black hole started as a large macroscopic thing. So can somebody look up how much is, let's settle that for once. How much is 1 M Planck in joules? Let's settle this. So that means in joules, but it'll be it's a C square, right? So it'll be some, so 10 to the minus 5 grams. That's right. So, and that is equal to, in joules, can we figure out? Let's write it once and for all, and I'll try to remember it. I should have looked at it up yesterday. I said the same thing. I made the same bungle yesterday, but I didn't fix myself. So, but at least this is good to know. So it's good that one person who is interested in phenomenology takes the correct answer, and we are all 100. Yeah. Oh, okay. I kind of nailed it by accident. So okay. So anyway, so that's what we have. That's what we have. Okay. So so the point is that yeah. So that's not much, and you want to encode all the initial state information into this. That's it seems like we arbitrary amount of information should be storable into a mass of into a piece of matter of this much. Yeah. 10 to the 9 joules? Right, yeah. So is that true? Okay, 10 to the 9. Okay, I mean, I'm not going to do any multiplication. 10 to the 9 joules, right? Okay, so I was clearly wrong. My victory was short-lived. So anyway, so that's the, yeah, that's true. I mean, G is, yeah, I mean, if you compute, it's possible. Anyway, so this is it's still not much. Right? It's still not much. So that's the general problem that we have. It's an arbitrary amount of information should be storable in a finite amount of matter. So, and that's why we don't like remnants. So the idea that something is left at the end of evaporations, we generally steer clear of it. And the other possibility, which is the one that Hawking initially preferred, is that after evaporation, it basically becomes, there is information is lost. That the pure states do indeed evolve into thermal states. So this was his hypothesis, which we don't believe because we have at least one example of holography, which is that quantum gravity, we seem to have a unitary theory which explains it, which just seem to be dual to it, and there is an enormous amount of evidence for it. Okay, so I think it is unlikely that there will be room for ADS-CFT to be correct while at the same time in violating unitarity. Okay, it's yeah, I think it is unlikely. So, and because of these two reasons, the remaining conclusion that we were led to was the fact that our untrue state that we wrote down for for this collapsing state that we had. So essentially, so this is our picture, and so we assumed a certain state for our the Hawking photon after the shell had collapsed. Okay, and so there was this, basically I wrote down the explicit form yesterday as well. I mean, I'm not going to write it again, it's a little bit long, but there is a contribution that is coming from here, which is called which is the outgoing part, which is basically we assume it's a thermal density matrix, and then there's an ingoing part which we assume to be in the vacuum. So that's essentially the untrue state. Okay, so and the key point was that, so the ingoing part we assume to be thermal. And the way in which we hope to get out of it, right? So the way in which the third resolution, which will be the one that we will kind of try to justify or defend, is that so what we will try to defend is that this thermality is only apparent, in the sense that the thing that we talked about yesterday is that if you have a complicated state and simple operators, and we spend some time talking about what exactly complicated means, etc. So then this can approximately look thermal. Okay, so this is a fact about Hilbert spaces of complicated quantum mechanical systems. So the assumption is that the way in which we may be able to sacrifice or salvage unitarity is that instead of what we see here as the apparent untrue state is in fact some complicated state in quantum gravity, which in low energy bulk effective field theory, which is another name for gravity coupled to quantum field theory in the bulk, looks like this thermal state. So this is the way in which we hope to salvage Hawking's information paradox. And it has not been fully successfully done, as I said, but we hope to, there are various ideas, and we definitely are, I think, making progress. But it's still not a completely solved system, largely because of the fact that the UV complete description of gravity is not completely under control. So that's really the problem, because it's not somehow enough to, we have good ideas, various good ideas about how this might emerge, but in order to really solve the information paradox, we also have to have full control, or at least some amount of control on what that state is. And that's a state, at least at the fundamental level, it's a state in quantum gravity, and so we don't have that much control on it. Okay? So yeah, so that's why it is both a useful idea as well as difficult to make progress in. So those are the kind of things that we said. So today what we want to talk about is we want to discuss sort of the primitive version of what is the most basic example, or the simple example of what a firewall would be. Okay, so we want to talk about firewalls, and we kind of want to talk about Page's theorem a little bit. And our class will be a little bit short today because I have to leave, but so these are the two things that I hope to cover in today's lecture. So let me explain what a firewall is in the context of Minkowski space first. Okay, so let's consider. So for instance, we wrote down when we discussed Rindler and Unruh and Minkowski and all that, we wrote down the vacuum state of Minkowski in this form, right? Okay, so this is what we have. So this is what we wrote down as the state of the Minkowski vacuum, and so this is this essentially the key point here is that this is coming from our assumption of smoothness of the Rindler horizon. Okay, which is basically the statement that Minkowski space is continuous, roughly speaking. Okay, and that is what we assumed in order to do our path integral in the Euclidean language to get a nice state on that entire Minkowski slice. So this is one thing we could look, but instead, so this state has no firewalls. A firewall is basically some kind of a discontinuity of some form or energy of some form at the location of the wedge. Okay, so if this location, if the entanglement structure of the Hilbert space here with the Hilbert space here is not precisely correct, you will expect to have, generically speaking, you will expect to see huge energy at that boundary. So, and I'll explain why in a second. Okay, so the point about this state is that it is precisely entangled in such a way that that situation is avoided. So there is a delicate entanglement structure between the left side and the right side, so that if you compute the Hamiltonian, for instance, in this state, we know that the Hamiltonian of a scalar field theory, if you compute in the vacuum state, it is 0. And you can explicitly check it here. You plug it in with the Hamiltonian for the scalar field, or you write it down, and I'll show you a mini calculation in a second. So if you compute it, you will see that it is 0. Okay, so but that is not the case, for example, for a generic state built from some state here and some state here. It has to be specifically entangled. So let's consider instead a state where instead let's consider some generic state, like let's say rho is equal to rho L tensor rho R. Okay, where rho L is the left, some density matrix on the left side, and rho R is some density matrix on the right side. Okay, let's consider something of the kind. And so where, right. So this is, you can think of this as basically the trace, you have traced out one of either of the wedge, if you want to think of it this way, but it's not very important. So you can think of these as the reduced density matrices that you get by tracing over each. So that this is some density matrix and this is some other density matrix, but it's not very important. What I'm going to say will generically be true. Okay, it's only for states with specific entanglement structures, like the vacuum or states built on the vacuum by acting with local operators. Those kinds of operators are the ones which will not have a firewall. So all other states do not have the nice entanglement structure that you're seeing here. So, and because all of them will have firewalls. Okay, so and yeah, so the key point, however, about these two states, the reason why I picked these two states as opposed to some other random state on the left and some other random state on the right, is because an observer restricted to either side will not be able to tell the difference between these two states. Okay, because the observer who is only doing measurements on IR will not be able to tell a difference, because as far as he is concerned, the state is rho r. Right? So because of which this state, for a guy who is sitting here or a guy who is sitting just here, these two states are identical. So you really have to have crossed this region in some sense in order to actually detect the difference in state that between these two states that I have written down. So that's the reason why I've specifically written this, but the existence of the firewall, I want to emphasize a generic property. Okay, so if you do any kind of a murderous thing to this state, you will end up finding some problematic thing. Okay, so I mean, of course, it doesn't have to be the ground state. It can be some excited state where you're acting with the local operators, etc. But that's fine. But as long as your state is, of this type, you will actually see that the observers on either side kind of say the same thing. And the key point about this is that this state has a discontinuity at x equal to 0. So this is what defines sort of the firewall. So what that means is that we can make an estimate about how much discontinuity is there, or the claim is that there is some kind of an energy, a huge amount of energy sitting at the boundary at x equals 0. Okay, so that's the claim. That's the claim of firewalls, and we can estimate how much is that energy, essentially because what this thing is arranging when you have an entangled state is that there is a kind of a delicate correlation between the things on the left and the right. Okay, so what this is doing is that it has completely gotten rid of it. So whatever happens here and whatever happens here, and that's it. These two are factorized states. Okay, so what that means is that you can expect that. So if you let's say the difference in the value of the field, this is a sort of a crude crude calculation. So delta phi, where phi is my scalar field, across x equal to 0 will be of the order of the UV cutoff of the theory. Okay, so in other words, it will basically go as 1 by epsilon, where epsilon is some cutoff. Okay, so yeah, so this is what the fluctuations you expect to be of this order, very roughly. Okay, is that okay? So, yeah, I mean, yeah, so what that means is that, so now what we can do is we can compute the actual energy contained in this. You can compute this, we can compute the expectation value of the Hamiltonian in that state. Okay, so let's do it. So this means that dx of phi at x equal to 0 is basically of the order of 1 by e square. Okay, so so you can compute the h, and so note that the Hamiltonian is basically an integral over the entire spatial slice, but everywhere else it is going to pick up 0. Okay, because this state is indistinguishable from the vacuum at everywhere except at x equal to 0. Okay, so that means that you will have a dx. There is an integral on the dx in the full Hamiltonian, but only the contribution is only going to be picked up from dx around x equal to 0, and then there is an integral over the d square y, and then there is this dx phi square. Okay, so and this basically will give you epsilon times d square y by epsilon to the 4, which is some area, okay, by this, where area is the area of this, whatever is the transverse direction. Okay, so that's what we will have. So, yeah, so, is that fine? So, and this is, so the point is that, so that is essentially the energy. Note that this, you should not, you might have seen A by some various epsilon things in entanglement entropy and all that. That is not what I'm computing. I'm computing energy here. Okay, so the point is that if you compute this Hamiltonian, the energy of this system with this unentangled state, you end up finding that you have like this divergence. Okay, so this is the statement. Okay, so that's what we are going to do here. Epsilon is basically the cutoff in scale. So here I am a little bit being too glib here actually. And I'm being glib because Harlow is being a little bit glib because I'm following his lectures. So here, this epsilon, the cutoff this is the variation in the field, right? So this field is, it depends on what the dimensionality of the field is. But the statement that there is a firewall does not really depend on what this particular guy is, because you will still get a divergence. Even if, let's say, the fluctuations in phi, for instance, in the scalar field, the scalar field depends on which, for instance, in 1 + 1 dimensions, the scalar field doesn't have, dimensions. Okay, so it's not quite correct to say that the fluctuations in the field are 1 by epsilon, but in general it will be some anything higher than 2 dimensions will be some 1 by epsilon some power. So because of the dimensionality of the field, but you can take this to be in 1 + 1 dimensions. You can take it to be constant, but even then you will get a 1 by epsilon here, and then the compact dimensions will contribute something. Okay, so the area is very important for this. Okay, so that's the way in which this thing will work. So you will basically, for instance, here, if you are a little bit more, want to be conservative, you can reduce 1 power of epsilon here, but you will still get a divergence. Okay, so that's the statement. So that's the reason why we say that there is a firewall. So yeah, but that's So this particular statement that I'm making about what the fluctuations are for delta phi is, that depends a little bit on the dimensionality of the thing, but the rest of the things are independent of it. Essentially, the crucial thing that you need is that I have a derivative, twice derivative with respect to x, but then I'm multiplying only by dx. So you'll always get one factor of something going on. Okay, so yeah, so that's basically what you get. So that's the firewall. Okay, so that's essentially the firewall. The firewall is essentially a statement that the entanglement structure of space-time somehow has gone through some ringer. That's the statement. So again, this is a divergent energy. This is a divergent energy at x equal to 0. And that is what is basically called a firewall. And it's essentially due to the fact that in order to break the entanglement structure in a quantum field theory, you need an infinite amount of energy. And so the statement that black holes may have firewalls is essentially the statement that when you have two Schwarzschilds here, okay, if you have an eternal black hole, at the horizon, somehow the situation is so dramatic that you're breaking the entanglement structure of space-time. That's what, roughly speaking, it means. So the question is whether, but on the other hand, principle of equivalence tells you that the space-time is smooth over there. Okay, so the question is whether which of these should one believe is the question, and I think the conservative standpoint at some level, at least for many classes of states, many classes of black holes, is that the horizon is smooth. So how to get it is a real question. Okay, so essentially because you can construct a state like this. Okay, so you can construct it, which is what the Hartle-Hawking state is. Okay, so yeah. Yeah, so and let me also emphasize that this is also true because this is just the ground state of our quantum field theory. Okay, so okay, so any questions on that? Any questions on that? Okay, so now what we are going to do is so now we'll in the next couple of lectures we'll talk about various sort of
So,
yeah.
Is this type of tensor factorization possible in any kind of state? Like, if I write a vacuum like this, and I will see that there are no firewalls.
You mean like this kind of state? So I didn't quite understand the question. So you're asking whether this. So in if you have a Hilbert space is always allow entangled states, right? If you construct your Hilbert space out of some spins like I was discussing yesterday, then you can always write some entangled state. So the question is not that whether you can construct some entangled state, the question is whether the state that under consideration for dynamical reasons, whatever they might be, does it have the entanglement structure that is required to avoid the firewall? That is the question. So ground states typically have ground states of like quantum field theories have entanglement structure of this kind. So the principle of equivalence, we interpret it as the statement that in the bulk space-time, locally it has the structure of Minkowski space. Essentially that's what, like even here there is gravity. So, but just the presence of gravity doesn't mean that, somehow still nonetheless there is bulk effective field theory applies, right? So the LHC is a pretty good instrument. So if you compute 2-point functions locally, you would find the 2-point functions that you find in Minkowski space. So that's essentially that sort of thing will be automatically guaranteed by this. Okay, so and that's what we are saying. So the question is not that, as I was saying yesterday also, the entanglement is not a statement about Hilbert spaces, it's a statement about states. So if you have a generic Hilbert space, of course you can have entangled states as well as not entangled states. A Hilbert space as well as a factorization. There's as a preferred factorization. You choose some factorization, you start with some Hilbert space, then you will have, you can have entangled states or not entangled states. But I'm saying that the kind of states that generally speaking for local quantum field theories, the Hilbert spaces of, the eigenstates of these systems are generally speaking entangled in the local basis, by which I mean the spin basis in the Ising model example. Okay, so that's a property of local Hamiltonians that their eigenstates are entangled in the local basis. You understand what I'm saying? That's essentially the process of diagonalization. So when you take a Hamiltonian, let's say Ising model Hamiltonian, and diagonalize it, what you're really doing is going from the local basis of spins to the basis of eigenstates, where the eigenstates are by, essentially by construction, essentially by structure of the thing is entangled. So that's the question. So I don't know whether I answered your question, but very roughly speaking, I mean, you can always write down unentangled states in this kind of thing. Of course, there is even one more subtlety when it comes to quantum field theory, which is that you only have algebras of operators. So as I said, it's something that is kind of becoming more popular nowadays. So, but this calculation is kind of like, it's a slightly more heuristic calculation, but it contains the essential physics. Even in quantum field theory, there is a notion of entanglement. It's just that you have to write it in terms of the algebras of observables instead of states. There are no states associated to subregions in quantum field theory. There is only states associated to the entire, you can associate, the Hilbert space has states, but the Hilbert space, there is no Hilbert space that you can associate to subregions in quantum field theory. So that's a property of quantum field theory. But still, these kinds of statements are, they're not so heuristic that they're useless. They're still meaningful. So for instance, the temperature that we compute is, under root temperature is a meaningful thing. Okay? Yeah, so I think I said enough words. I think you can parse it in some useful way. Yeah?
Can you understand how to get from entangled state to product state?
No, here I'm saying that I'm considering a specific product state. So this is an entangled state. And I'm saying that this entangled state has the property that if you compute the Hamiltonian expectation value in it, it is 0. So that's an indicator of no firewalls. Okay? So, but here I'm saying that let me consider some other state. I could have considered any other state, but I'm specifically considering this particular state because observers living on this side or this side will not be able to distinguish between this state and this state. Because if I take a trace of the left side, I'll get the right density matrix. Because this is basically the, what we were usually, this is, let me just define it. I wrote it last time. So this is trace over L of omega. So this is what this rho of R is. So that means that a guy who is living on the right Hilbert's right wedge will not be able to distinguish by doing experiments that are localized on the right wedge to distinguish between this state or this state. Okay, so that's what is interesting about this state in particular. But generic states will always have firewalls. Okay, so generic states typically always have firewalls. So, and that's like, it's almost built into, so you really need the, if the black hole is, so that's one reason about, there is a question of the typicality of, firewalls for black holes. So here you can, so in a very basic sense, the problem is that unless you construct a delicate state like this, which has fine entanglement structure across the horizon, you end up finding firewalls. Okay? Because if this is these two guys, it can have some other entanglement also. It should have this specific entanglement or something similar to it by acting with local operators in order to not have a firewall. Just because you have entanglement doesn't mean that you will not have a firewall. You have to have a very specific kind of entanglement adapted to the Hamiltonian of your system in order to escape firewalls. So, but I'm taking this particular state for the reason that for local observers on either wedge, this state and this state are indistinguishable. Okay? So yeah, but that's, I think it's, your question kind of brought out some points that I probably was worth emphasizing, so that's good. Okay, any other question? Yeah.
How was this the consequence of this? Like, why is delta phi out of UV cutoff from this, like, taking a generic state?
So that essentially just a statement that if you have some generic configuration, quantum field theory is basically about fluctuating quantum fields. Right? So you expect that if you have two random states in quantum field theory, the value of the field on each of them will not be correlated, and they will generically be as wide away as they can be, which is basically the controlled by the UV cutoff of the theory. So this, to make this completely tight, I have to give phi some kind of dimension. Otherwise, it's basically, phi is not directly related to the, the scaling dimension of, like it's better to make, in 3 plus 1 dimensions, for instance, this will have some 1 plus e to the, e to the, what is it, 1 by e, basically, I think, 4 minus 2 by 2, yeah. So it'll be something that will happen. So, okay, in 4 dimensions, for instance, this will be exactly 1 by e, epsilon. Okay, and I think that's probably the reason why Harlow is taking it to be 1 by epsilon. But I'm saying that it is not, it's not related, at least not, it's not just that the dimension is, yeah, I mean, it can be dimensionless if it is 0 plus, 1 plus 1 dimensions. But the point I'm making is not related to this particular value of the fluctuation. The point is that there is fluctuation. That's the point. In quantum field theory, or in a generic state, the value of the field, it will be different. Right? And the difference is typically whatever is the maximum range allowed. So that's the generic value of the difference. And that generic value is what I'm writing here. So, and then the rest is basically taking derivatives across this discontinuity. Okay, so, so now let's go on to, so any other question? From yesterday or today? Okay. So let's go on to, one ingredient that we want to talk about today. So unfortunately, I'll have to, have half an hour. So I'll have to leave a little early today. So, yeah, so this is, so what we want to talk about, so we'll talk about a few, well, not disconnected, but related facts. So, sort of to build the story of how information, we want to phrase the information paradox. So I think the one goal of this lecture, by the end of this lecture, I think it'll be good if we can formulate the information paradox in a modern form. I think resolving it, I think once I do that, I think you will be able to go and look it up, and then you can, resolving in the sense, at least, the resolving in the sense that people claim to have resolved it. You know what I'm saying? So that I think you can go and look at various, I can give you some reading material or whatever, and you can write your reports on that. Okay, I think that, so in the context of both flat space and ADS-CFT, we have like the current status of information paradox. If we can make a clean statement, I think that's like a worthy goal for how to conclude these lectures. And maybe, we can have some occasional digression here and there, but I think it is, more than that is probably too much to ask. So anyway, so we want to put in some collection of tools in order to make that discussion sort of smooth, and one of them is Page's theorem. Okay, so, and we'll discuss Page's theorem, and then I think we will close it for today. So, and I won't quite get to the Page curve today, but it's a small extension, and that I will talk about in the context of more, this is more of a digression. This is a tool in some sense from entanglement entropy and so on. Okay, and then we will use it coming back to black holes in the next lecture or so. Okay, so let's consider a Hilbert space which is factorized like this. Okay, so two Hilbert spaces combined together, HA tensor HB, it can be some spin, some other spin. But the point is that unlike in the case of spin, we assume that both these Hilbert spaces are large dimensions. Okay, so that we can make some genericity statements. So, and without loss of generality, we will assume this to be the case. Okay, this means, means dimension of the Hilbert space. Okay, so this is, you can choose it to be either, you choose one, A to be less than B. And so I want to make a definition of what is called a maximally entangled state. And this is, let's assume a general state in the Hilbert space is some mixed density operator. Okay, so we are not even assuming that the general state here is a pure state. We are just going to assume some generic density matrix. So rho AB is a general state. So whenever I say state, sometimes it will mean pure state, but in many cases it will actually mean mixed state. Okay, so density matrix. So is pure, but rho A is defined to be this, is proportional to the identity matrix or identity operator, the identity operator on A, operator on HA. So in other words, the state is completely mixed if you trace out one of these tensor factors. Okay, so that's what is called the that's what is called a maximally entangled state. Yeah, so there are a few variations of Page's theorem. So let me
why are you saying this mixed after you take
that's the definition of maximally entangled. So I am saying that if you take a generic state on this Hilbert space and trace over one side of this, the density matrix that I'm left with, which is this guy, is diagonal. It's basically 1, 1, 1, 1. So there is no information in that state. So that's why that is interesting. So that's what makes it maximally entangled. So, like, yeah. So the statement is, so this is just a definition, and it is, like whether it exists, whether it doesn't exist, none of this is being stated here. We are just saying that, if you take a state like this, and then you trace over some part of the Hilbert space, A or B, then this is true. So in many cases, such states may not exist. Okay, I'm not saying that, like, this is just a definition. If it happens, this is true. We haven't even shown that it must exist. We haven't shown that it exists. So, but what Page basically says is that if A is much smaller in size as a Hilbert space than B, then this is almost always approximately true. This is the statement that he's making. Okay, and I will make those qualifiers precise. Okay, so Page's theorem, intuitively, that's what it says. It's saying that if A, this Hilbert space is much smaller than B, then if you do a reduced density matrix, so this reduced density matrix of a generic state in A, okay, we have to make what generic state means slightly more precise, but for a generic state in A, if you reduce, if you take the trace over this guy and forget about this, whatever is left here is essentially a random state. Okay, so that's what the intuition behind Page's theorem is. And what that really means is that, if you have an entangled system, there are two entangled systems, one of which is very large compared to the other. The smaller system is most of the states that you will find in the Hilbert space. The first guy will look random or thermal. Okay, so that's essentially the statement. It's here it is really trace rho A is like really random in some sense. It's not even beyond thermal. Okay. So, yeah, so let's state Page's theorem. So, so a generic pure state. So let me first write it. A generic pure state in HAB leads to almost maximally entangled rho A as long as A is much less than B. Okay, so one version of the statement, so the version that Page proved is the one where he shows this statement, okay? So I'll define what the left hand side means in a second. So this is what he showed. So, and let me define what these things are. So, integral of du is normalized to 1. Okay, so du is what I'll explain what u is a unitary operator. And essentially what we want to say, so whenever we want to make a statement about average, or generic states, what we do is we average over all the possible, roughly speaking, average over all the possible states in the Hilbert space and then hope that that statement is true on an average. Okay, on the Hilbert space. So that's what we are, I'll make that a little bit more precise in a second. So, and so this SA is nothing but rho A. Okay, as long as, so yeah, so this is a statement. So Page's theorem, the version that he proved is basically that the entanglement entropy of rho A is almost that of a random state or a maximally entangled state. That's what he's showing. He's not quite showing that the state itself is maximally entangled necessarily. So in order to show that, we'll have to prove a statement on norms in Hilbert space. Okay, which will also kind of, that is the one that people prefer nowadays. So, but this is the statement that Page proved. Okay, so he showed that entanglement entropy of this of a generic mixed state, generic reduced density matrix, if of a subsystem, if the subsystem is sufficiently small, is that of a maximally entangled state. So that's essentially what he showed. So let's make the statement a little bit more precise. The proof is not that very interesting, but it's not very hard either. But yeah, so let's. Okay, so let me define what, I already defined what A and B, absolute values of A and B means. It basically means the dimension of the Hilbert spaces. So now, so this SA, I'm sure you have seen. This is just the entanglement entropy. There is nothing really more to say there. It's just, that's the definition of entanglement entropy. I mean, it has been an object that has been studied ever since Boltzmann. Okay, so this is sometimes called Four-Neumann entropy. Okay, so, and the thing that I really should explain to you is what am I doing with this integral on du. Okay, so that's the thing that I have to explain to you. So let me explain that. So what I'm doing is I'm introducing the notion of what is called a Haar measure. I won't define Haar measure completely precisely, but I'll give you an example so that it is sort of intuitive to you. Okay, so in general for Haar measures are basically natural measures that you can introduce on unitary groups. Okay, and the reason why, okay. So, yeah, so unitary groups, so you can do integrations on manifolds, that you know that, right? So Lie groups are also manifolds. And there is, so in order to do an integration, you need a measure. So, and the natural measure on the Lie group manifold is basically what is called a Haar measure. Okay, so for instance, for SU2, SU3, SO3, SO4, all of them, you can basically construct their appropriate Haar measures. And I will show you, I mean, you have implicitly sort of used these things already in some sense. But, so that's the idea. Basic idea is that, so, and the reason why we care about UN, unitary group, is that we want to view a generic state as U acting on some fixed state where U is arbitrary or chosen at random. That's the, okay, so this is fixed. And this guy sort of traverses the entire Hilbert space if you choose U randomly. Okay? And this U is basically a unitary in the dimensionality, or if I'm acting on a unitary in the state, actually okay, let me not, because it is, I'm really acting on a unitary on the full, this thing. So let me just say U acting on a Hilbert space A has dimension HA. It's a dimension HA times dimension HA matrix. Okay, so it's a humongous matrix. Okay, so it's a humongous matrix, and the reason why this is what are we interested in showing? We are interested in showing that there is some statement that we expect to be typically true in the Hilbert space of the theory. Okay, and what do we mean by typicality? Typicality means, so let me write a statement, maybe that will make it a little bit clearer. So to prove that some property holds on a typical state, holds on a typical state, we integrate over all of these unitaries, over all of these unitaries. So this is the general philosophy, and okay, so what we mean by that is that to show, so let me give you concretely what it means. To show that some property holds in some property called f holds on f typical state is x. So let's say we want to show that. Okay, so what we'll do is we'll do this on f acting on u of psi naught is equal to x. This is what we show. Is that clear? So that's what it means for the state to be typical. Okay, so the statement that a typical state has some property is the statement that if you integrate over all the unitaries, while psi naught, it doesn't matter psi naught what it is. Okay, because psi naught is, if you integrate over all the u's, no matter where you start, you will cover the entire Hilbert space. Okay, so and that's what this du means. So the statement that you have a typical state has a specific property is basically the statement that if you integrate that property over the entire unitary group, that property holds. Okay, so it's not, you should not think of it as an, it's a bit different from saying that it's not that it's a property that you're computing on a given state on an average or something like that. That's not what it is. What it is if you pick a generic state, which is another name for typical state, and you compute this quantity, overwhelmingly likely, and if then this is the value that you can expect to get. Okay, so in order to really show that this is the value that you're almost certainly going to get, you also need to show that the variance of this quantity, this f minus that guy squared, is 0. Or 0 or very small, typically very small. Okay, so that's what you have to show. So then you can say that typically this is a property of the states. Is that clear? So my statement was precise, but I don't know whether I think you understood it, right? Yeah, okay, so that is, so that's what basically we are going to show. That's the reason why we are doing this integral.
In quantum mechanics, it's like unitary operator is exponential minus IISc.
Yeah, unitary operator is for time evolution. But this I'm talking about the general unitary. So if you take one random state and another random state in the Hilbert space, you take some state and some other random state in the Hilbert space, the unitary that connects is not necessarily a time evolution. Yeah.
Yeah, I'm saying that in that case, du will be just dt.
Yeah, exactly. So in that particular case, yes, that's yeah. So that is true. Well, I mean, yeah. I mean, it depends on the h also, but yeah. So so it's what did I want to say? Yeah. So now, so this is the statement that the statement that I showed you that what's his name? Page proved is the entanglement entropy statement. Okay, so but there is a stronger statement that is also true, which I think is more in the spirit of many of the discussions nowadays. So I'll write it like this. Okay, so note that I am not proving those statements that I wrote down, but they're not very hard to prove. I'll give you a general rough idea how to prove them. Okay. So what I showed you, what I argued in the, what I stated regarding entanglement entropy is that the state has the entanglement entropy of a generic state or a random state. That's what I showed. But you can actually show that the state itself is close to a random state. So, and this is why you need a norm. So this is a norm in the Hilbert space, and then you're computing that norm, and then you're saying that, that is less than this quantity. So if A, the dimensionality of A is much less than B, then this will become increasingly close to this random identity. This is the identity operator on the Hilbert space A. Okay? So
what is this notion of inner product on the space manifold of unitaries?
It's a vector space, right? So it's not inner products kind of, norms are defined on vector spaces. So manifolds have metrics and vector spaces have norms. So we are going to define that. So let's define what that norm is. So let's say you have a matrix M, okay, living in some Hilbert space. Okay? So this is defined as trace of M dagger M. It's that simple. Okay, conceptually it's very simple, but because of the square root involved in this operator, it's a bit hard to work with. Okay, in fact, the proof of this kind of statements, or the entanglement entropy type statements, is really about, this is sometimes called the L1 norm. Is really about translating this L1 norm statement, and L1 norm states are useful because you can interpret them as a statement that measurements done on them, the eigenvalues that you will get, will be close to each other. So that's somehow the physical notion of closeness of a state. Okay, that's why we like L1 norms. But L1 norms are hard to work with because of the square root that is sitting inside this guy. Okay, so generally speaking, they're harder to work with. So what instead one often defines is something called the L2 norm, which is square root of trace M dagger M. So this is an L2 norm. Okay, and the good thing about this is that this, the M dagger M is trivial. There is no subtlety about taking that. Trace also is just adding all the diagonal values, and then taking square root is also trivial. So conceptually this is completely trivial. Here the square root is a little bit tricky. Okay, because the matrix square root. So this is what we would like to work with. So the trick in proving these theorems, as I said, is that you do some standard things, whatever, like, Cauchy-Schwarz like inequalities, in order to rewrite this inequality as a statement about an L2 norm, and then you just directly do that integral over du, which you can do because you know many things about this unitary matrix integrals. Okay?
The meaning of the norm is being changed from L1 norm to L2 norm. Like, what's the norm we defining it? Like, you said that would be a norm of that
See, the norm has to basically just satisfy some few properties. The notion of a norm in vector space, it has to satisfy something like triangle inequality. It has to be positive, a few things like that. You know what I'm saying? So both of these you can show that if you look at a vector space book and you look at the definition of a norm, both you can show are acceptable norms.
There must be some other definition of norms that also satisfies those.
There are infinite number of norms, right? I mean, you can define many norms of notions of distance. You know what I'm saying? I mean, there are, so the notion of a distance in vector space, there are many. So there are many. But it's just that two of them I'm emphasizing because this is the one that quantum mechanically is a statement about how, if you do measurements on states, the results, the eigenvalues that you get as a result of measurements lie close to each other. So that's the physical notion of closeness. I'm not telling you that, I'm not proving to you that that's actually implicit in this, but it is true. Okay, so L1 norm has the property that you can translate that into a statement about measurements. So which is why closeness of measurements. So that's why this is interesting. But I'm saying that that's not an easy norm to work with in proving these inequalities because of this, this pesky square root that is sitting there. So what we do is we translate it using some, algebraic manipulation or some inequalities, well-known inequalities like Cauchy-Schwarz or something like that. And then we reinterpret that as a statement about the L2 norm. And the L2 norm we can typically do directly. These integrals oftentimes are directly doable. So what you do is, the integrals over u, that, because this is what is called the Haar measure. I mentioned the Haar measure. It's basically a measure on integration on these unitary groups, and they are doable explicitly once they are typically written in terms of this M2. So that's the technical point. But so otherwise this M2 norm is not very interesting for us. Okay? So that's the statement, and so for instance, if you want to measure the difference between two states, let's say two density matrices, this is the norm that you would use. So if you want to have a notion of closeness of a state to one another, okay, the physical notion of closeness, that's what you would use. Okay, so So this is the statement. This really shows that the state itself, after doing this reduced density matrix over the bigger system, is essentially random. Okay, this shows that. The previous statement, the Page's theorem, which is what he wanted to show for the case of, let's say, in the context of, Page proved his theorem in the context of information paradox. Okay, where he was thinking of one system as a black hole and one system as a radiation that is leaking out of the black hole. And we will talk about related things and show Page curve and all that in next class possibly, or maybe the next after. So, but the point is that in order to show that, he only needed a statement about entanglement entropy of the state and not a statement about the closeness of the states themselves. Okay, but I'm saying that this sort of arguments are very useful nowadays, as I'm sure you have seen in that paper that I gave you. So, many of these kinds of statements automatically come in handy. So that's why I'm emphasizing this. Okay, so this is a statement about the closeness of the state, and that's what that is. So now I just want to, so I'll close the class by just saying one thing about, I'm not going to define Haar measure in full generality, but from what I said, it should be kind of clear to you that it's not a surprising thing that you might have it. Okay, so I'll just give you an example of Haar measure for SU2. So Haar measure for SU2 is easy to define. Note that, so in even in large dimension cases, there are many integrals with Haar measure integrals are actually possible to do. Okay, so that's just a fact. So there are papers written on it. There is a resource that you can rely on, and that's the reason why, even though this, I'm going to do it only for SU2, but this is for very large n by n matrices. Okay, so but still you can make statements about its integrals are still can be usefully made. So that's the reason why this is doable. So, but you're not going to work with explicit Haar measures to do that. Okay, you're going to work with some, you can make general arguments quite easily actually. So, anyway, so the Haar measure for SU2. So, what is SU2? SU2 is, so what is the group manifold of SU2? Do you know? Anybody knows? I'm sure many of you know. Only those who don't know should answer. It's a S3. SU2 as a group manifold is S3. So this I will leave as an exercise. This is part of any first lecture on spin and so on for this spinners and so on. Like usually that's where we start. So I have taught this many times, so I'm not going to repeat it. Okay. So this is we'll just take it as a fact. So but the interesting thing about SU2 being S3 is that now we can get a state. So S3 you can define in this way. So that means now S3 is nothing but fine. It's just the complex numbers with mode 1. So that's what S3 is. So now we can parameterize. So I'm trying to give you an explicit measure. Okay, so I can parameterize using the standard spin kind of parameterization that often people write. Okay, so now I have theta, phi, and chi. You can see that it's a three-dimensional space. R is just the extra coordinate that is living in C2. Right? So, so now I can just induce my metric, induce my measure from the standard measure on C2. Right? So this is a standard measure on C2, and I can do this is again a small exercise. You do a Jacobian calculation using this coordinate transformation that I've told you, and you will find that this gives you R cube times sine 2 theta, d theta, d phi, d chi, and this guy here is what is called the Haar measure on SU2. Okay? So, and that's it. Okay, so and I think that unfortunately I have to go a little bit early, so but I think this is a good place to stop. Any questions? Okay, if not, we can close it.